Hi there, guys. Well, welcome back. This is the start of Unit 4 in the HLAA Oxford Mathematics book. And Chapter 4 is called Measuring Change and Differentiation. Now, there's a lot of people who will have seen differentiation in some other course, either a bridging course from GCSE, for example, or IGCSE, it's in there. And so you might be thinking that to start off with here, you're on pretty solid ground. You think, okay, this is good. I know lots of stuff about this. I'm going to crack through the first few exercises. It's going to be really simple. In fact, it starts off with the algebra of limits and continuous functions. So there's 4 exercises here, which build up with pretty new concepts, really, before we get into some of the differentiation that you might be aware of. Okay, and then, when it comes to differentiation, they've got differentiation by first principles. So, that's, for example, taking the function f of x equals x squared and working out from first principles. So not just using a formula. So from figuring out using the algebra of limits, the derivative there is going to give you 2x. Okay, and just having a look down at some of these other micro concepts here, we're seeing it's talking about tangents and normals to curves, differentiation rules, methods for differentiation, chain rule, product rule, quotient rule, maxima, minima, and points of inflection, some of which we've discussed before, kinematic problems, optimization, and implicit differentiation. Now, the other part of calculus, other than differentiation, is integration, and that's not turning up in this chapter. So that's essentially the inverse function to differentiation. Okay, just to say as well that before chapter 4 and at the end of unit 3, chapters, whatever you want to call them, we have a little investigation here on making a Mandelbrot. So making fractals using Mandelbrot sets. And this is using complex numbers. It's a nice little investigation. It leads you through a little bit here. I mean, this could extend potentially to an IA, to a piece of coursework, although a lot of this will simply be learning stuff which is out there already. Okay, so I'm not going to do that, and I'm going to skip through before you start, you should know the skill checks things, because, to be honest, we've seen all of those things earlier in the previous units. Okay, now, again, there's a little exercise here, and again, I'm not going to do this. This is Zeno's paradox here, and if you have a little look, for a second, and this is quite nice. I'll set it up, but I'm going to go into limits pretty much straight away through the questions. So I'll set this one up. If you want to skip forward, you can, but this is pretty interesting, I guess. It says, about 2,500 years ago, Zeno of Elea, philosopher and logician, posed the following problem. Achilles and the tortoise were running a race. Achilles allowed the tortoise a head start of 10 meters. Both started running at a constant speed, Achilles at 10 meters per second and the tortoise at 1 meter per second. How many meters would Achilles, after how many meters, would Achilles overtake the tortoise? But Zeno says, well, in fact, he's not going to overtake the tortoise, because Zeno's argument is saying, well, if Achilles starts at point A and runs to the tortoise's starting point, point B, as you can see in the little diagram there, and which is 10 meters from A, when Achilles reaches point B, the tortoise will now be a meter away because he runs at a speed which is a tenth of what Achilles runs at. So the tortoise is still a meter away. And now, likewise, when Achilles now runs to the tortoise's new position, still at the same speed, when he gets to that new position, point C, he'll find that the tortoise is now a tenth of that 1 meter away. He'll be 10 centimeters away. So he still wouldn't have caught him. And if you keep doing iterations like that, it appears that Zeno will never catch the tortoise. Okay, now that's a paradox because, of course, you're thinking, well, in real time, obviously, if he's running faster, at some stage he's going to pass the tortoise. Okay, now that all sounds quite obvious, but you can set up the mathematics in both ways. And I think they say somewhere here, and they take you through this investigation, which is quite nice. And it says here, it has taken several millennia for mathematicians to arrive at the language and concepts needed to solve this paradox satisfactorily. So, I mean, it's not good enough to say in mathematics, well, it's obvious that it's going to pass him at some point. We need to prove that in some way, or prove that he doesn't in some way as well, but through the language of mathematics. Now, I'm not going to go into this at the moment, but this is kind of interesting to do. Again, I have seen this done in pieces of coursework. The problem with doing this in pieces of coursework is obviously because this has been studied to death, frankly. So this is out there. There's many analyses of this situation. You know, you're not necessarily going to get much further or extend this very interestingly in your own direction. And to think of how to extend it in your own direction as well is going to be hard. So, you know, it's easy to find a piece of coursework or a piece of work or analyzing this. And, you know, if you handed it in as a piece of coursework, who's to know that it's yours? So I wouldn't necessarily suggest that as a piece of coursework. Coursework, we'll talk about later, hey? Okay, limits of functions. So limits of functions, and again, there's another investigation here. Let's discuss this one briefly too. Still not getting to the questions. And so they're saying, use your GDC to plot the function of x squared minus 1 divided by x minus 1. Now, okay, you're looking at this function and you're thinking, okay, well, this can't be defined when x is equal to 1. However, when you plot your table here, you'll realize that when you put in 0.9 and when you put in 1.1, your answers seem to be approaching each other. They're not tending towards infinity. And so when you find that out, you'll see that, in fact, as you approach x is equal to 1, you seem to get out the answer of 2. Let's put that on Desmos, okay? So we've got x squared minus 1 over x minus 1. So let's put this one on. Y equals x squared minus 1 and divided by x minus 1. Here we don't want the bracket there. On the bracket there. Sorry. Y equals x squared minus 1 divided by minus 1. Okay, so that's what the function is looking like. So we're aware that the function can't be defined when the denominator of a rational function is equal to 0. Now, in this case, it appears to be defined. You don't have any asymptotes in this situation. You can see that there is the point plotted here of 1, 1, and that appears to be on the line. Okay, and so the point of the table that they're coming up with here is to say, well, we're heading towards 2 from both sides. Okay, so let's just see what they're saying here. So here we go. So let's just steal this thing here. And there's kind of definitions. So this is a kind of odd situation which we've got. This goes against what we've been talking about before. So this is kind of new. It's talking about what's the limit as x tends to a. In this case, we're talking about x tending to 1, but we're saying as x tends to this 1 in this case from the negative side, so from the left-hand side for this f of x. And so if we say that with this function here, if we say x squared minus 1 over x minus 1, then that's going to give us the answer of 2. So if we're tending to this, to the answer of 2 from the left-hand side, and if we're also tending to the answer of 2, I'm just going to type in that function, writing that function just to make it a little easier, from the right-hand side. So this is coming in from positive x, and this is coming in from negative x, to get to the point of 1. Okay, so it's getting to 1 from different sides. If this exists as well, then that means to say that the limit overall exists as well, as long as this is the same as this. Hang on a second, that might be a point which is taken later. It says from the left, and this means this is approaches from the right. And leaving out the sign says that A indicates that the limit is the same from both directions. Yeah. So this is just saying that as well, that the limit exists. And so therefore, the limit when x tends to 1 from either side, okay, of this function is equal to 2. So there is a limit which exists. Okay, right. Now, that doesn't necessarily mean that we have a coordinate point at x is equal to 1. For that to exist, we need to look at the next exercise, which is talking about continuity. Okay, so continuous function. So we're just going to leave that where it is at the moment. Okay, so example number 1. And example number 1 says, using your GDC, sketch the graph of y is equal to 3x minus 1 over x. Okay, so again, let's take this one here, and let's take the function which has been plotted on the GDC as well. Okay, so let's take part A. And again, we're looking at this and we're thinking, okay, well, when x is equal to 0, what's happening to this function here? We should be getting a divide by 0 here, and it should be meaning that we're getting an asymptote in the normal situations of rational functions. Now we can see here we've got the similar situation to the example above, in that this one is saying 3 to the power of x minus 1 over x actually appears to give us this point here. Okay, now the question is asking, so we've sketched the graph there, sorry, and by the way, they've defined this function saying that x is not equal to 0. So we're not considering when x is equal to 0 here. We're just basically saying, does this limit exist? Okay, does the limit exist for this, and the limit exists for this, and therefore, if it's the same, what's the limit for this thing here? Okay, so does the limit overall exist as x tends to 0? Okay, so find the limit as x tends from the negative direction to 0. So we're asking, as we tend in this direction here, what are we going to get out as the answer? Now you can clearly see from the graph, and you could check this numerically as well by putting in very small values very, very close to 0. You can see that as you get closer to 0 from the negative side, you're tending towards, I think it's 1.1. And again, you can put in very small values to try that one out. Okay, let's just check with the there. It says from the table of values, right? So they're suggesting that you come up with a table of values. And you can come up with that by going to the statistics function and typing in your function, and then coming up with a list, a sequence of numbers there as well, essentially. I'm not going to do that now, but you can do it on your GDC as well. Okay, so from the table of values, or in other words, from putting in numbers which are closer and closer to 0, you can see that you're getting out 1.1. Okay, so we say that the limit as x tends from the negative side, this function here, is going to become 1.1. So it's equal to 1.1. And likewise, the same when we're tending from the positive side. Okay, now they're saying that this is approximately 1.1, presumably because, in fact, we're not ever getting out the answer of 1.1, and maybe it's not exactly that. And so we don't know necessarily, we don't have enough information either from the table or from or from the values which you're putting in. Now you could say that that's equal to 1.1 if you go closer and closer and you find out your next decimal places from both the left-hand side and the right-hand side, say for example putting in 0.001, and hopefully that's giving us an answer which we can give to one decimal place. So we could say that this is exactly equal to this if we just take this one a little further and check that on both sides that's working. Okay, so we can get rid of the approximately equals to if we just take our decimal places a little bit further. Let me just check this one. Okay, so let's just put in, let's, for example, put in 0.01, 3 to the power of that, minus 1, and divided by 0.01. Let's see what we're getting out from our table of values. So we've got 3 to the power of 0.001, subtract 1 there, and then divide that by 0.001. Yeah, so that's giving us an answer of 1.099 and so on. Now, presumably it's not going to go any way further off this. The closer and closer we get, if we're limiting this from both sides and we're getting to the same number, if we're tending to the same number, and we can say that we're equaling something to 1 decimal place, if we get enough decimal places. Okay, right, I'll leave that one there. Now, in example 2, it says use your GDC to plot the function here. So we've got this piecewise function, and you'll notice that this is not being defined when x is equal to 1. So that's not included in our domain. In fact, our domain is x belongs to the real numbers, but x is not equal to 1. Okay, and they want us to find the limit as x tends to 1 from the negative direction. So we can see pretty easily from this graph what that's going to become. So it's going to tend towards this number here. And as we come from the positive direction towards 1 from the positive x side of the axis, then we're going to tend to this number here as well. Now, the question as to whether this function is continuous or not is a tricky one. And again, we'll see that next time. But you might just say, well, this is not a continuous function because we can see that there's a break. But in fact, the fact that we're not actually including x is equal to 1 in our function means that we actually do have a continuous function on either side. And again, we'll see that in a bit. That's the same, in fact, with x's, f of x is equal to 1 over x. We'll see that in the next exercise. Okay, so anyway, what is this going to tend towards? So you can see that as you're tending towards 1 from the negative side, for this function here, we're talking about using 2x minus 2 there. And you can see that that's going to become, well, think about putting 1 in here. And this is continuous all the way up until this point here. So, you know, there's values of x, there's values that you can get out for f of x for all x that you're putting in here. And you can see that it's just a straight line graph. So when you're putting in 1 here, even though we're not defining it at 1, we can say, well, what happens as we go towards 1? Well, you can see that that's going to give you 2 times 1 take away 2. It's going to go towards 0. And you can see that clearly from the graph as well. Now, for the other side, you see that the limit as x tends to 1 from the positive direction of this other function, 2x plus 1, you can see that that's tending towards 3. Okay, and again, you can just sort of eyeball that. You can see it from the graph. And you can actually put 1 in here, even though we're not actually defined, it's not actually defined at 1. Okay, now we're done with that. That is done, but there's a little point which is turning up later, and that's to say that, in fact, in this case, the limit as x tends to 1 doesn't exist for this function because it's not the same for both of these. Okay, and that's turning up in the next point, I think. Okay, so there we go. There we're getting our answers there. They're not overthinking this one, really. Not doing too much work there. And here we go. This is the statement, which is then now saying that the limit exists as we tend to see. Okay, so the limit tends towards this number as we tend towards C from either direction for x. So that's our x here. There's some C here. When we go from the negative direction, as long as we get to the same answer, let's call it the answer L up here, as long as we're getting to this answer from one direction and we're getting to this answer from the other direction, in whichever way it's coming to, then the limit exists for x tends to c. Okay, and that's what it's saying here. It's difficult to see. It says x tends from the positive direction and x has to tend from the negative direction to the same number for this limit to exist without us saying that it comes from one direction to the other. Okay, so there we go. That is the end of that for exercise 4A. So you can have a look at the questions from 4A there. There's a little hint on the side. I know I've mentioned this one before. The double arrow, which you're reading in the formula there, is an implication sign in both directions. It means if the thing on the left-hand side is true, then it implies the thing on the right-hand side. But when we say if and only if, the only if reads the other way around. It means the thing on the right-hand side has to imply the thing on the left-hand side as well. Okay, so it's a double implication arrow. Okay, well, I'm going to continue with this with the limits of continuity just to get in 4B as well. There's not an awful lot in 4A. And there's a nice little investigation in front here as well, which leads to, okay, so some good stuff there, which leads to these 2 points about continuity. Now, this is pretty dry, to be honest. It's hard to read this and think about what's going on without doing a question. But I will read it now, and I will go through it a little bit now as well, and then I'll come back to it after the question as well. So if you want to flick to the question first, go through the question, and then come back to this, well, I'll go back through it again at the end too. So let's have a look at this, and I'm going to take all of this, I'm going to try and make some sense of it. And it says that there are 3 necessary conditions for f to be continuous at a particular point. So at the start, we're just saying that is x continuous at a particular point. Now, what do we mean by continuity anyway of functions? We're saying, for example, straight line function would be continuous. Now, we kind of know that. We mean that it's got no breaks. And we know it just, the line is continuous. In other words, you can put your pen on the page and keep drawing and not take your pen off the page and get to the end of the line, or maybe the line continues into infinity, but you're not going to have to take your pen off the page. In fact, that is formalized in this definition down here. But first of all, we need to think, well, what does it mean to be continuous at a particular point? The same with maybe a cubic, cubics. And all polynomials are continuous because they're defined for all values of a, and actually because of all of these conditions here, and because of these conditions here. I'm loath to say because of one thing, because in fact this is a big definition. Okay, so first of all, we need to define what it is to be continuous at a particular point. So for example, if I put in a and I get out an answer, does that mean to say it's continuous at that point? Well, you can think of situations maybe where you're thinking, well, hang on a second, what about if the function is defined only for natural numbers? Now, is that continuous at that point? So there's no number just to the other side, there's no answer just to the other side of either of those things as well. So, so here we go. What does it say? First of all, f has to be defined at a. Okay, so there has to be an answer. When you put in a, this function has to take a and do something with it. Okay, so first of all, f has to be defined at a, and a is an element of the domain of f. Okay, that's the first point. That's the point that people often forget, in fact. Quite obviously, there needs to be a function which applies to a. Okay, now the second point says that the limit of f at a exists. Okay, now remember the limit is defined to be from both directions. So as we're tending to a from this direction, we should say that the limit of f of x from both directions is the same value. In this case, they're talking about L, the value which is coming out. Okay, so the limit has to exist. And so that wouldn't exist in that case where I was talking about natural numbers, for example, the domain only being existing for natural numbers, well, it wouldn't exist as a limit from either side coming into that point because there's no definition for the points leading up to that. Okay, so there has to be the limit existing, and finally, that limit has to be the same as f of a. So this has to be f of a, and there we go. We've kind of said everything on this graph here. We've said that we have to have something acting on A to give us an answer. That answer has to be equal to f of A, and the limit at that particular point, as x tends to that particular point for the function, has to be equal to this L, which is equal to f of A as well. Okay, now if you can find, so a function that is not continuous at point A is said to be discontinuous at point A. Now, if you can find an element in the domain where we are discontinuous, then the function is not a continuous function. It's a discontinuous function. Okay, right. Now let's have a look at how we define the function to be continuous. Now, these are very subtle points here, and you know, I look at this and I think this is just horrible to read through. I'd much prefer to do an example, but let's read it through. A function is said to be continuous on any open interval I if it is continuous at every point in the interval. Okay, so an interval could be, for example, x is greater than 1. And that would be an open interval as well. That's tending towards infinity. Okay, and then it says a function is continuous at if it is continuous at every point in its domain. So this thing here for particular points has to be true for every point in its domain. Then it says as well the function is continuous everywhere if it is continuous throughout the real numbers. So if it's throughout the real numbers, and again, you know, you're thinking, well, you know, if you're getting points which are only defined for natural numbers, then we definitely can't find our limits to those particular x values, if you like, your a, the limit to a for this function, because, you know, we don't have any values right next to the point itself, you know, infinitely close to that point itself. Okay, so we've got three definitions for a function there. It's saying a function is continuous if it is continuous for every point on the open interval, if it is continuous at every point in its domain, and if it is continuous throughout the real numbers. Now, in an exam situation, if you were saying, why is it continuous? If you're being asked that, then I think I would just write down, well, it is the function is continuous at every point in its domain, and you'll probably just get away with that. But and the domain accepts all real numbers as well. Okay, within that interval. Okay, and it says, of course, that a function is not continuous. A function which is not continuous is said to be discontinuous. Well, that's just a definition there. And again, it's sufficient to find a point in the domain where it's discontinuous in order to say that the function is discontinuous. Now, there you go. That's fairly interesting. And then we get to this point, which I was mentioning earlier. So it's fairly interesting. It's probably quite a hard read. Now get to this point here, and it says, note that the reciprocal function is a continuous function. Wow, okay, well, so we're saying that this function, this one here, where we're tending to positive infinity and to negative infinity as we're tending towards 0 from both sides, we're saying that, in fact, this is a continuous function. Well, it is a continuous function, in fact, because we're taking out x is equal to 0. Now, if you said y equals 1 over x, all values, all real values, well, first of all, it wouldn't be a function because it wouldn't be defined for this value here, okay? But then even if you were allowed to say it was a function, it would be discontinuous. But this is continuous because this follows the rules. The rules are saying that in fact it's continuous at every point in its domain. Whatever point you take, you can tend to if you take the limit at that point, it will tend to that point. And yet you can't take this point here. You think, well, why don't I take a point which is, infinitely close to this? Well, you'll still get, I mean, infinitely close is kind of a concept really, but a point which is extremely close to this, but you'll still get a value, and a value which you can tend towards coming from one side and tend towards coming from the other side as well. And of course, it will be defined at that point, and the function 1 over x exists for that point, so it's continuous. It follows the rules of being continuous. And then it says, well, however, it is not continuous on an open interval containing 0. Yeah, but it's also not a function at that point. So, that's a bit of a moot point. Okay, then, example 3 asks us to plot this graph here, which is a piecewise function. And then it asks us to find the limits at the particular points. And it asks us then to find out whether f or f of x is continuous at those particular points. The points being this point here, and this point here. Now, you can pretty much answer that last question just by looking at the whole thing, but we're going to need to do this in mathematics. But you can see that you can probably guess that it is continuous here. That it definitely is continuous here because that's just a continuous function. And a sort of linear functions, your basic linear functions are continuous functions. Although we'll need to show that, and you can see that we're not continuous here. So ultimately, this is not a continuous graph. Okay, you can also see that this is defined over all real values because we've got a definition between -1 and 1, and the other part of the domain just says otherwise. So for example, when x is equal to -1, we're definitely getting a point here, and that's coming from the otherwise. And when x is equal to 1, we're definitely getting a point here at 1, 2, and that's coming from the otherwise again. But then from the original function, we can see that we're actually getting an open circle at x is equal to 1 because it's not defined at x is equal to 1. Okay. So, although this one seems quite obvious, we're going to need to do this mathematically. Now, the graph is fairly straightforward. Make sure you're putting your open circle and your closed circle there. You don't need a circle here because you can see that it is defined at that point. And in fact, it's continuous either side. So, find the limits, if they exist, as x approaches. So we're looking at B now. X approaches -1, 0, and 1. So let's look at the limit. Let's do this completely and say, well, as x tends to -1 from the negative side, we're using this function. But the limit of that doesn't depend on x at all, so that's just equal to 2. That's no problem. In fact, that's a good point, actually. If you say the limit of, x tends to 1 in this function here, x -1, you can split that up. Because this part doesn't involve x at all, you can split that up into the limit as x tends to 1 of x, and then simply -1 on the end. Okay, so you can split up your terms there. But that will probably turn up later, to be honest. Okay, and we're going to look at x tending to +1. Sorry, not +1, -1 from the positive direction. And in this case, we're going to need to use this function here because we're essentially coming up the line here. And so that's going to be equal to, function is going to be equal to -2x in that case. And again, we can see pretty easily from the graph what that's going to tend towards. You can come up with a table of values for yourself if you want, but it's pretty obvious that this is a continuous function and that you're tending towards 2 as well. Therefore, the limit as x tends to -1 of this function is the function. The function is defined to be both things, because piecewise is equal to 2. In other words, the limit exists. Okay, now for the bit in the middle, I feel like that's pretty dull to do this, because it's essentially the same function in the middle, which is clearly a continuous function. So I think we can get away for that second one, for when x is equal to 0, for saying x tends to 0 of our function is simply equal to 0 there. Now let's just check what they do in the book there. Let's see if they've gone any further for that. And yeah, actually they haven't even gone from the left-hand side and the right-hand side for part B, for the first part, so they haven't even done that. So yeah, that's fine. They've just written that here. Personally, I would have stated this because that gives us our definition of there being a limit which exists. Okay, and for the last part, again, I would do this thing here, and I can see that they've done that in the book as well. So again, we can say the limit as x tends to 1 from the negative side, and the limit as x tends to 1 from the positive side. Now we can say, I'm going to just write f. No, I'm not. I'm going to write here 2 because that's coming from this side. That's how the function is defined. And then we've got minus 2x in there as well. Now we can see that these are tending to two different things. So this is tending to 2, and this one here is tending to minus 2. Therefore, there is no limit as x tends to 1. F(x) doesn't exist, does not exist. Okay, so that one doesn't exist. Okay, and you can see the book is saying, yeah, it doesn't exist or it's undefined. Okay, now for the next part, we need to remember our definitions of a continuous function. Now I'm going to flick back to the definitions again, just to see that there's 3 conditions necessary for a function to be continuous at particular points. First of all, it has to be defined. So f of a has to be defined. Secondly, the limit has to exist at those particular points. And thirdly, the value of the limit also has to give you f of a. It has to give you the height at that point as well. Okay, so let's look at this then. And let's look for the first point for x is equal to minus 1. And I'm going to save myself a little writing out here, but we can see that we've got the points 1, 2, and 3. And so let's just say f of a exists was the first point. The limit exists at a and at a, and also the limit is going to equal to f of a. So there's our 3 points. I'm just going to check through these rather than writing things down each time. Okay, so for the first one, so for the first part here, for when x is equal to minus 1, let's just write down 1, 2, 3, and put ticks and crosses. Well, when x is equal to minus 1, yes, f of a exists because the function is defined for all real values. So in fact, for all of these things here, and let's do x is equal to 0 and x is equal to 1 at the same time. 1, 2, 3, and we've got 1, 2, 3. So for all of these, the first condition is met because this thing is defined for all x belongs to real numbers. Okay, then it says determine whether. Then we have to check the second part. It says does the limit exist at a? Well, we've already found that out from the first parts. Yes, it does exist for x is equal to minus 1 and x is equal to 0, but it does not exist there. So now we can see that this one is just not a continuous function at that point. Okay, but let's go a little further and let's look at the third part. Now, does the limit equal f of a? Now, did the limit equal to f of minus 1? And f of minus 1 was equal to 2, and that was our limit as well. So yes, it did in that case. And yes, it did in this case as well. And the limit didn't exist here, so we can't answer this question. So that's not applicable there because there is no limit to set equal to f of a in the first place. So whether or not it's continuous, now we can say yes, continuous, no, not continuous. Now, obviously, you'll need to write that one out, And you can see how the written that one out as well. And you can see the way in which that's defined it as well. But essentially, it's gone through the same steps as I've gone through there. Okay, right, example 4. And now we're talking about a function which is kind of similar to where we started when we said x squared minus 1 divided by x minus 1. We're getting something very similar here. And this piecewise function, again, is saying we've got this function on the top divided by x minus 1, and the function is equal to k when x is equal to 1. It says determine the value of k such that f of x is continuous at x is equal to 1. Now, you might just think, why don't I just substitute 1 into this function here? Oh, by the way, there's a little mistake here. That should say x cubed there. Okay, so you might just say that, why don't we just substitute 1 in here? Well, you can see that when you substitute 1 in here, you're going to get this divide by 0. And so that's going to cause a problem if you just substitute the 1 in. Okay, well, let's look at this on Desmos as well. So there you are. I plotted this one on Desmos too before I started this video. And you can see that, in fact, this is giving you a quadratic here by the looks of things. And again, that we are defined at 1, 2. So it appears to be defined at this point. And it appears to be a continuous function. Okay, well, so determine this value. Well, let's play around with this a little bit here. And I'm expecting that the x minus 1 is going to be a factor of this thing here. And in fact, another way of seeing that is by looking at putting f of 1 in. You can see that you're clearly getting 1 minus 3 plus 5 and minus 3 there. So we're getting an answer of 0. Okay, and if you're getting an answer of 0 out, we definitely know that x minus 1 is a factor. That's the work we did from last time around. Now, but remember, there's a point which we've made a couple of times now already, that if the coefficients of all of your powers of x sum to 0, then you definitely know that f of 1 is equal to 0. Okay, so f of 1 is equal to 0 there. So therefore, we can use Horner's algorithm, and we can put in 1 minus 3 and 5 and minus 3 to do the synthetic division, which we learned in the previous unit. And we can put in times by 1, bring the 1 down, put pluses here, and 1 times 1 is 1. Add those two things together, we're going to get minus 2. 2 times 1 is minus 2. Add those two things together, gives 3. And 3 times 1 is equal to 3. Add those two things together is equal to 0. And you can see that that's giving us our factor because we're ending up with this remainder of 0 there. Now our quotient is this part. So we can now say that our function on the top part here is actually equal to x minus 1 and x squared minus 2x plus 3 as our quotient, divided by x is minus 1. We can see that this and this cancels, and we could perhaps factorize this thing here. Maybe it doesn't factorize actually, but either way, we don't need to here. And there we go. So this is a little bit of working out for what our function can equal to if we do this division, so long as x is not equal to 1. Now we can look at our limit. So we can say, what's our limit as x tends to 1 in this case? So as x tends to 1 for this function is the same as if we divide by this and this, and we're allowed to do that because x is not actually equal to 1. And since this is just a continuous function here anyway, as all polynomials are, then you can just substitute the 1 in here, and you'll get out your 1 take away 2 is minus 1, plus the 3, which is equal to 2. So determine the value of k such that f of x is continuous at x is equal to 1. That value of k has to be equal to 2. because our limit on both sides is tending towards 2. So remember, in that graph which I drew, we're getting this point at the bottom, 1, 2, but we're tending to 2 from this side, and we're tending to 2 from this side. Now, in order for you to define this as a function, this part here is necessary, because obviously when you put in equals to 1, you have a problem. So it's not defined at this point here. So even though when I draw this graph here on Desmos, it appears to be defined at 1, 2, in fact, it's not defined there unless we come up with the function, f of x equals to 2, and then we put in for x equals 2. Now, Desmos doesn't like that, but we're just defining that particular function. So not for x is equal to 2, for x is equal to 1. Okay, now Desmos doesn't like that to write in one particular point, but that's essentially what we're doing in this case. Okay, now again, you can't really zoom into that point and find that there's a missing point, because there are points which are infinitely close to that point, so it will plot those points. And so however close you zoom in, you are still nowhere near to getting infinitely close. So the graph will obviously look continuous, but in fact it's not continuous unless you say that x is equal to 1, when x is equal to 1, f of x is equal to 2. Okay, so this is not quite the same as this thing here, and that's quite a subtle point, to be honest. But although this simplifies to this, it only simplifies to this under the conditions that we're not actually equaling to 1. Okay, so this function is not equal to this function, but it turns out that it is equal to this function here if you then define this bit here as well. So now this function is equal to this function here, but we need to define our point when x is equal to minus 1. Okay, right, well, I'll stop there. There's a lot to go through, and there's a lot of quite theoretical work there, I think. And so this is theoretically difficult. It's not necessarily algebraically difficult. Okay, then, guys, well, have a go at exercise 4B, and then we've got 2 more exercises on limits before we get into the differentiation fully. Okay, then thanks for listening, and hopefully see you for the next one.